In August of 2024, a research team at Northwestern University published a paper that quietly rewrote what we thought was possible in construction. They did not announce a new chemical compound. They did not patent a new synthetic material. They took ordinary beach sand, saturated it with seawater, ran a mild electrical current through it, somewhere between 2 and 4 volts, less than an AA battery, and watched loose grains fuse into a solid, rock-hard mass in minutes. No cement, no mixing, no kiln fired to 1400 degrees Celsius, just electricity, sand, and the ocean. Professor Alessandro Rota Loria, who led the study, described what he saw in those first laboratory experiments the way someone describes watching the impossible happen in slow motion. The sand didn't just harden, it transformed. It became something else entirely. Dense, cohesive, structurally sound. Something that looked and behaved like natural stone, because that is precisely what it was. Not manufactured, not fabricated. Grown from the minerals already dissolved in seawater itself. The paper was published in Communications, Earth, and Environment, a journal in the Nature portfolio. It was peer-reviewed, independently verified, and confirmed by mineralogists. The science was airtight. And then, the way so much genuinely important science does, it settled quietly into the archive, while the world kept buying bags of Portland cement at $30 a pop. This is where this story begins. Not with conspiracy, but with a question that deserves a serious answer. When a process this significant lands in one of the world's most prestigious scientific journals, backed by the Army Research Office, verified by a team of physicists and engineers, why does almost no one building infrastructure today know it exists? The answer requires going back much further than 2024. It requires going back to 1976, to a German-born architect named Wolf Hilberts, standing underwater off the coast of Texas, with a mild electrical current running through a metal frame he had built himself. Hilberts wasn't a chemist. He was trained in architecture, which is perhaps exactly why he approached the problem the way he did. He was obsessed with a single question that most engineers never thought to ask. How does a coral reef build itself? A coral reef is structurally harder than most commercial concrete. It grows in the harshest saltwater environments on Earth. It repairs itself, it gets stronger with age, and it builds itself from nothing but seawater and electricity generated by living organisms. Hilberts thought, what if you didn't need the organism? What if you could replicate the chemistry with a simple electrode and a low-voltage current? He ran the experiment. He placed 2 metal electrodes into seawater, connected them to a low-voltage DC source, and let the current flow. What happened next had never been documented outside of biological systems. Minerals dissolved in the seawater, calcium carbonate, magnesium hydroxide, a complex mineral called hydromagnesite, began precipitating out of solution and depositing directly onto the cathode, layer by layer, crystal by crystal, building up a dense, solid, load-bearing structure from water. He called it mineral accretion. The world would eventually come to know it as biorock. By 1979, Hilberts had published his findings in the IEE Journal of Oceanic Engineering. By 1981, the United States Patent Office had issued him a patent for large-scale structural mineral accretion. The compressive strength of the material he grew measured between 3,120 and 5,350 pounds per square inch, comparable to the concrete used to pour sidewalks, parking lots, and low-rise building foundations. It could be shaped into any form. It could be powered by solar panels floating on the surface above it. And crucially, it required no extraction, no mining, no combustion, and no factory. Hilberts spent the rest of his life pursuing this technology, building artificial reefs across more than 40 countries, demonstrating structural applications, partnering with marine scientists to prove what his electrode could do. When he died in 2007, more than 500 biorock structures had been built worldwide. His work was eventually exhibited at the Museum of Modern Art in New York. The scientific community acknowledged his contribution, and the construction industry ignored every word of it for nearly 5 decades. To understand why that matters, you need to understand what we are currently doing with cement and what we are paying for it, in money, in carbon, and in coastline. The global cement market reached over $407 billion in 2024. The broader concrete and construction materials industry eclipses $1.8 trillion when you account for ready-mix, precast, and structural applications. These numbers are not just impressive. They describe a system so deeply embedded in global infrastructure that it has become structurally invisible. We pour more concrete every 3 years than was poured in the entire 20th century combined. China alone consumed more cement between 2011 and 2013 than the United States did across the entire 1900s. And here's the cost of that dependency that no quarterly report chooses to lead with. The cement industry is responsible for approximately 8% of total global carbon dioxide emissions every year. That makes it, as an industry, the 3rd largest source of hard-to-eliminate CO2 on the planet, behind only load following electricity and steel. Producing a single ton of cement releases roughly 900 kilograms of CO2. The process that releases it isn't an inefficiency that engineers haven't solved yet. It is inherent to the chemistry. You cannot make Portland cement without decomposing limestone at high heat, and that decomposition releases carbon dioxide as a fundamental byproduct of the reaction. There is no version of conventional cement that is carbon neutral. It is chemically impossible with current processes. When climate targets demand a 16% reduction in cement emissions by 2030, the industry responds with carbon capture proposals, supplementary cementitious materials, and incremental efficiency upgrades, all of which cost money, all of which require new infrastructure, and none of which change the fundamental chemistry that has been releasing carbon since the first bag of Portland was mixed in the 1820s. Meanwhile, in 2024, Rata Loria's team at Northwestern sat down and did the math on their electrical method. The cost to cement 1 cubic meter of marine sand using electrodeposition, $3 to $6. The cost of conventional binders used in comparable coastal applications, up to $70 for the same unit volume. That is not a marginal improvement. That is an order of magnitude in cost reduction, achieved with no carbon emissions, no mining, and no proprietary chemical compounds. Only electrons and the minerals the ocean already provides for free. The mechanism behind why this works is worth dwelling on, because it is one of the most elegant pieces of applied electrochemistry in recent engineering literature. Seawater is not just water. It is an electrolyte solution loaded with dissolved ions: calcium, magnesium, bicarbonate, chloride, sulfate. These ions are the same building blocks that every coral, every clam, every oyster in the ocean uses to construct its skeleton. The chemistry to build with them is already present in the water. What is missing is the energy to drive the precipitation reaction. When a mild electrical current runs between two electrodes submerged in seawater, it locally raises the pH at the cathode, the negatively charged electrode. At elevated pH, calcium carbonate loses its solubility. It can no longer stay dissolved. It precipitates out of solution and nucleates directly onto the surface of the cathode and, crucially, onto any granular material, sand, in the surrounding zone. The mineral crystals don't just coat the sand grains, they grow bridges between them, interlocking across the void spaces in the granular structure and cementing the entire matrix into a coherent solid. At 2 to 3 volts, the dominant deposit is calcium carbonate, the same mineral that forms the Great Barrier Reef and every oyster shell on Earth. At around 4 volts, the reaction shifts to favor magnesium hydroxide and hydromagnesite, a mineral found widely in natural stone formations. Rata Loria's team was the first to document hydromagnesite forming in this electrodeposition process. No one had seen it before in similar experiments. The material that results, depending on treatment duration and voltage, reaches compressive strengths of several megapascals, within the range of weak concrete, with hydraulic conductivity reduced by an order of magnitude, meaning water flows through the treated sand with a fraction of the ease it did before. The team also demonstrated that the entire process is reversible. Flip the polarity, swap which electrode is the anode and which is the cathode, and the localized pH drop dissolves the minerals back into solution. The rock becomes sand again. A material science process that is undoable on command has implications that extend far beyond construction. It suggests programmable ground, infrastructure that can be modified, repaired, or removed without demolition equipment, without excavation, without generating the approximately 1.3 billion tons of construction and demolition waste the global building sector produces every year. Rata Loria's team is not the only group working in this space, and the convergence of parallel research threads here is striking. At the same time that electrodeposition of seawater minerals is gaining traction in civil engineering, a completely separate field, biocementation, has spent the last 2 decades developing an equally radical approach to building without cement, this time using microbiology instead of electricity. Microbially induced carbonate precipitation, or MICP, works by introducing a specific bacterium, most commonly Sporosarsina pasteurii, into a body of sand or soil along with a solution of urea and calcium chloride. The bacterium produces an enzyme called urease, which hydrolyzes the urea into ammonia and carbonate ions. Those carbonate ions combine with the calcium in solution to form calcium carbonate crystals, which precipitate directly at the contact points between sand grains, fusing them together. In a landmark field-scale test, researchers injected these bacteria into a 100 cubic meter body of fine sand. The resulting strength reached up to 12 megapascals, stronger than some architectural concretes, grown entirely by living organisms at ambient temperature with no combustion, no kiln, and no emissions. A 2015 study at the University of Heidelberg demonstrated 100% larval mortality of mosquitoes in water treated with the copper byproduct of biocementation at concentrations 4 times below the World Health Organization's safe drinking limit. The biological implications of this chemistry extend in directions that construction alone doesn't begin to exhaust. What ties these two threads together, Hilbert's in 1976, the Northwestern team in 2024, the biocementation researchers testing bacteria in Australian sand columns, is the same underlying logic. Nature already knows how to turn loose, granular material into solid stone. Coral reefs do it, shellfish do it, limestone formations do it, sandstone does it, under pressure, over geological time. The scientific challenge was never whether the chemistry was possible. It was whether humans could drive that chemistry on a human timescale and at an engineering scale, without the temperature, the pressure, or the millions of years. The answer, it turns out, is yes, with a few volts and the right electrode configuration. This is Parker Sloan, and the question this research forces us to confront is one with very large stakes. The concrete and cement industry is not a villain in a simple story. It built the tunnels under rivers, the bridges across gorges, the water treatment plants that keep cities alive. It will continue to do all of those things. But the 8% of global CO2 emissions it generates, the billions spent annually on coastal barriers that erode and fail, the mountains of demolished concrete that become inert waste, those costs are now being weighed against a process that requires no new chemistry, produces no combustion emissions, costs $3 to $6 per cubic meter, and is reversible. Whether electrode deposition replaces cement entirely is a question future infrastructure budgets will answer. What it already replaces, the idea that building solid structures always requires burning limestone at 1400 degrees, that assumption is gone. The Northwestern study buried it in a peer-reviewed journal that any engineer with an internet connection can read before breakfast. According to the 2020 study by the European Commission's Joint Research Center, nearly 26% of the Earth's beaches will disappear before the end of this century. More than 40% of the global human population lives in coastal zones directly threatened by sea level rise and erosion. The conventional response is to inject cement into coastal ground and build seawalls that cost millions of dollars per mile, structures that themselves erode, that leach chemicals into marine ecosystems, and that fail catastrophically when the sand beneath them liquefies under storm surge pressure. Rotoloria's process can be powered by a floating solar panel. It can run on renewable energy. It produces no toxic byproducts. And it can be reversed if the community changes its mind about where it wants the shoreline to be. No other coastal protection technology in existence offers any version of that last capability. The biorock reefs that Hilbert's and his collaborators built in places like Pemuteran, Bali, now among the most celebrated coral reef restoration projects on Earth, have been standing for over 2 decades. They were built for less than the cost of a single section of conventional seawall. They grow stronger every year. They host thousands of species. And they were built by an architect who looked at a coral reef and asked one question that the entire construction industry had somehow never thought to take seriously. What if the ocean already contains everything you need? If that question hit you the way it should have, I want you to do 2 things right now. Hit the subscribe button because this channel is where these questions get asked out loud, where the science that doesn't fit the billion-dollar narrative still gets a fair hearing. And then share this video with someone who builds things, who studies oceans, who worries about coastlines, or who has simply spent too long paying too much for materials that the chemistry of seawater was already willing to provide for almost nothing. Every person who sees this video is one more person who knows the question exists. And the questions that get asked loudly enough always eventually get answered.